Hello, everyone. Welcome to MACSMIN 2025. It's a pleasure to introduce Dr. Andrea Daru, who will talk about computational tools for the prediction and generation of novel reticular framework materials. Andrea, over to you, please.
Yeah, thank you for the introduction. Yeah, today I'm going to talk about how one of my workflow that I suggest for the prediction of frameworks material that goes a little bit away from this trendy machine learning. I try to go back into something more intrinsic of the structure of this type of framework. Since it's a long talk, I made a little bit of an outline. I wasn't sure who is in the audience, so I gave kind of a little bit of an introduction about metal and covalent organic frameworks. Then I will talk about this paper, and then I want also to show how I'm thinking, how we can bridge the computational prediction with something like that is synthesizable, and we can write kind of a recipe to help also the experimentalists and ourselves to know if the structure is actually correct or not. So our reticular frameworks, usually called metal or covalent organic frameworks, are a class of crystalline porous material. They're basically linked building blocks. Usually MOF are in between metal ions and organic molecules, while COF are entirely organic. These building blocks, they reticulate in certain manifold that has certain name, and all of them, they follow certain topology. And this is what the main part of this talk will aim at. Both MOF and COFs are very famous, and because they can tackle various applications, from storage to catalysis to separation, and all of these properties can be by controlling the structure and the porosity of the final material. And that's why it's so important to predict the material with accuracy and mostly before the synthesis of such materials. But what are the benefits of MOF and COF? Well, the selective absorption, as I say, there are some of these material that they can absorb CO2 pretty well, or they can do water harvesting, for example, in desert area. Or for their capacity, since they are porous material, they have a very big surface area, so they can be used. The surface area can be used for that reason. And also because we can customize their design by choosing the metal center, so the nodes and the various linker, we can make them adaptable to that we want to. And then this is mostly related to COF, because they have a thermal and chemical stability. COF, they were kind of, in some sense and in some particular area, an improvement of MOF, because since they are covalent frameworks, they can resist thermally and chemically more than MOF, which they are coordinated linker to metal center. So a couple of examples of famous MOF and COF. I just selected 3, just to give like a show of the images. Like for example, HCAS1 is very famous for methane absorption. It's formed by like copper paddle wheel node and like 3-carboxylate, 3-carboxybenzoate linker. So we can see that we can create a very good topology with 2 different porosity. Also, MOF5 was the first one to be discovered. It can be good for like catalysis or, for example, gas storage. Like hydrogen is based on zirconium oxide node with this carboxyl benzoate linker. And one of the COF is, for example, COF 309, in which I was participating in the development and the computational prediction, which is a very good COF for water harvesting. Okay, after this little introduction, I can pass through the discussion of what the paper is about and what is their workflow trying to achieve. Okay, so the in silico prediction, it's sometimes not trivial, because having nodes and linker, it seems that having only 2 building blocks can give a very easy building of the final material, but in reality is not, because of how many connectivity, how many bonds they can create to each other, they can achieve different topology. And mostly because of the symmetry that the building blocks they can take, they can also reticulate in space differently. This workflow can be used for pre-synthesis or after the synthesis when single crystal are not available. So we have to rely on power X-ray diffraction pattern that they don't have 3D information into it. So we can use a computational build material, build MOF to overlap with the experimental PXRD. This workflow also tends to go a little bit away from high throughput or try to improve a high throughput. So instead of create hundreds of compounds and then having difficulties or choosing methods for optimizing that are not too accurate, this workflow tends to do the opposite, try to select a shorter list of possible material so that we can use them more accurate computation to have a better description and maybe study reactivity or absorption or whatever we need from that material. Okay, so in Sketch, their workflow is like this. So those are all the blocks that they create different operation. If you want to read more, this is the publication where also Davide is there, and I have to thank him because he suggested me for giving a talk at this conference, at this meeting. So okay, I will break every block of this workflow and I will explain one by one. So this workflow is also available online. So the first operation that we have to do is preparing our building blocks. So we have usually idea of the reagent that we are using. So we need to create a couple of files, one that contains the node and one that contains the linker. At this stage, since it's online on a small server, there is no optimizer available. So it's better if we give kind of a optimization based on the computation that we have available. For example, we can do DFT, force field, or anything to just adjust a little bit the structure. Then after that, so here is an example, for example, of what the workflow is expecting. For example, here I'm taking like a zirconium oxide node, which is very typical of certain MOF. This zirconium oxide node, they can have different connectivity, for example, from 12, 10, 8, or 6, and here I show them with the related name of the MOF to which they belong. So usually the building blocks for creating this type of material are made in this way, so like in a cluster way, and then we place ghost atom, usually called like X, to show where we want the node to connect. So the more we have connectivity, and then we can go lower. So the lower we have, the different symmetry we can achieve. So for example, if we have a 12 connected node, we might create MOF 801, but if we have only 6, kind of MOF 808. After that, we just open the website, we find this type of very straightforward UI user interface where we can just upload the node, upload the linker, and just click upload. And then the server will do some simple operation. It will do first an analysis. So it will take, for example, in this case, I'm taking as an example MOF 841, where the building blocks are this zirconium oxide that has a connectivity, and this tetrabenzoic acid that has 4 connectivities. So the first analysis is to see how many topologies we can have based only on the connectivity numbers, so based only on 8 and 4 connectivity. And as you can see, in this case, we have 29, which is not too much, but when we have to create the material and optimize all of them, it can become prohibitive if we want to use DFT. So what the workflow does is adding a couple of more operations, so filtering this type of topology, this type of potential material, by symmetry of the building blocks and by the occurrence that they can have. So the first filter is by symmetry. So not only the connectivity, but also the symmetry itself of the two, they can belong to a certain reticulation space or not. And that also can access a certain topology or not. So these filters are in their way. The list of topology are the one present in the reticular chemistry structure database called RCSR. And the name also is the same as implemented there. So here, for example, an example of what this tiny algorithm does. So the node and the linker, how they have been uploaded, they have a symmetry of, for example, D4H for the node and TH for the linker. But this concept is kind of a bit more loose than being very strict to the potential symmetry, because I assume that when the node and the linker, they are not like clustered in space, but they are bound to each other, the symmetry can increase or decrease. So the algorithm take care also to a higher symmetry, for example, OH of the node, or D4 lower, and the same thing for the linker, which is OH or T. And then it will try to couple all of these, each one of the three potential symmetry on the node with each one of the potential symmetry of the linkers, and see which type of pair they can actually create an existing topology, or otherwise it would be discarded. So in this case, the only is I chose this case I got the easiest case, because there is only one potential pairing up. So the OH symmetry of the node and TH of the linker, which together they create a topology called flu. And this is actually already published and is so we can have a confirmation from experiment that actually the generated structure from the workflow is in agreement with the structure from experiment and previously published. Then we can go a little bit more difficult. For example, there is another example of NU50. NU50 has a node that is based on indium tree, which has for connectivities, and a similar linker to the one before. This is just a pyrene with four connectivities. So again, if we upload these two files, the first operation will find D2H and D2H again as a main symmetry, but then it will consider also higher D4H and D2 for both. So this is a very curious case, because both of the building blocks can access the same symmetry. So we have again 29 potential topology, but then we don't have only one topology that can come out with these two, with the pairing of these 3 and 3 symmetries, but we have 7, which are listed here below. So in this case with 7, how do we know which one can be the most likely and the ones the less likely? So what I did is to add another filter that consider the occurrence of a certain topology from previous published MOF. So what I did was to download this database called the ARC database, which it included a lot of both simulated and experimental MOF. And then from all of them, I extracted the topology. And then based off how many occurrences we have, we can rank. For example, if I only look at the experimental MOF included in database, we can see that, for example, PCU, DIA, MBO, they have like sort of a distribution where certain topology are the most likely to occur and other the less likely. And then also, if I use the full database, where also includes hypothetical, so only computationally made MOF, then they are optimized. So the one they are taking into account are only the ones that are stable so that they don't collapse. We can see that we have, again, a similar distribution with other topology coming in. So the algorithm will take care of how many occurrences we have, and in this case, it will rank them. And so from this list that before was just a list of seven MOF, now we can say that, for example, PTS is the topology the most likely followed by the other. And we have actually a very good agreement experimentally, because also from the experiment, this topology is the one that actually we can see. And then we can also, another confirmation, let's say that we don't have experiment, we just want to do this prior to synthesis. So since we have only 7 potential structures, we can optimize them, for example, at the DFT level, and try to achieve a higher accuracy. So then we can rank them based on the energy that the DFT will give to us. And then we see that, again, the PTS topology is the one that is most stable. But also we can disagree sometimes with the ranking of occurrence, because the second potential morph is a bit higher in energy. The third one collapsed, and the fourth one actually is close in energy to the first one. So we can actually see why. And if we read the publication where NU50 was published, they noticed that the framework has some structural deformation after activation. So this for me was like a good insight to like thinking of probably this 2.4 kcal per mole of very slight instability is probably the explanation of why these two types of topology, they are very close in energy, and also both of them, they come out as a potential material from the workflow. So as a final confirmation, we can do a matching with the PXRD from the literature and from the one that we can generate from both structure that I'm showing here with the same color. So we can see that, as they say in the publication, as synthesized, we have this high feature at around 8, and then it moves after activation closer to 10. And this is in agreement with the two structures that the workflow made and then optimized via DFT. And we can see that the same green and the same red, they have a shift. It's not at the same high as the experiment, but we can see that the shift is similar. And this could be an explanation of what they can see. And then it's just a slightly changing reticulation, because these two topology, if you can see at the image, they are very, very similar. It's just a few twists that they make them apart. So this could be also useful to understand what happened experimentally when some post-synthetic activation or modification are being made on the material. Okay, but at this point you can also blame the fact that I picked this MOF. They were already published, so I do a little bit of a cherry picking of whatever it agrees with my workflow, and I take out whatever it doesn't. So to show that this workflow can actually work, I'm showing 2 MOF that we were trying to synthesize, and how we deal with the structure before synthesis. One is based on iron sulfur cluster, and another is based on zirconium side node, like MOF 841 I show first. But I will start with this iron sulfur cluster MOF. So here in Chicago, we are interested in creating MOF based on this type of node. And we made a couple of publications already trying to use this MOF for CO2 reduction and for like climate-related projects. But we noticed that when we use an iron sulfur cluster as a node, we always have like a 1D, sort of a one periodic structure. We never have a reticulation, like a 3D structure. So this was like one of the aim for our research, and try to see, can we actually obtain a 3D structure? So the workflow was very useful, because we can just feed a node and a linker and see if we can or we cannot. So in this case, here is just an iron sulfur cluster. Iron is in orange, sulfur is in yellow, and purple dots are where the nodes connect to the linker. In this case, the linker, since it's a research that, I mean, we can still consider I kind of hide it, but I can say that it's like a flat linker for connectivity. So if we feed both of them to the workflow, we find that the iron sulfur cluster has a C2 symmetry, because it's actually correct, because it's a pseudo-cubane, so It doesn't have a higher symmetry as we can think of, but the algorithm will also consider C2H and C1. And the same thing for the linker again, C2H and C4H and C2 will also be considered. And with all the pairing of 3 and these 3 with each of these 3, we can have again 29 possible topology, which since we have the same similar symmetries than before, they are the same the previous case, NU50. But after we look at the occurrences from the database, we see that only 5 of this topology can actually take place. And they are usually with the lowest symmetry of the aerosol for cluster. So from those, we optimize these 3, PPR, NOM, and FGL. And we made some experiment. Here I didn't make the experiment, but Nick Jean, which was a postdoc in the Professor Anderson group here at Chicago, made the synthesis, and he gave me the PXRD pattern, which is here in gray. And then extracting the pattern from this tree MOF, we can see a few peaks, they can overlap with the peaks that we have experimentally. And the pattern that overlaps best is the green. So I understand that for the crystallographer, probably in the audience, this PXRD, they don't overlap the best. But since it's a computational optimized, we always have some deviation from whatever has been optimized at the DFT level and what is actually in the experimental PXRD. But just adjusting the lattice vector later, we could have a better overlap. But this is just to show that we just uploading a couple of small files and just retrieving or creating ourselves the related topology, we can have a good prediction. But unfortunately, this when we try to scale to create like this MOF and to see in reality with type of topology we have, the framework was created like in a very, very low yield. So we don't have a perfect confirmation like from like single crystal or other technique to confirm this actually the PTR topology prediction is there. And this is actually something that happen pretty often, the fact that it's difficult to really have a match with from experiment and computation. So we are still working on it, but yeah, it's difficult. So we will see if I was right or not. But as a second example, lately we decide for other type of projects that we have to synthesize other MOFs. So we wanted to have a zirconium node and a cyclohexane link. So I create both of this file and upload it. So this is actually this slide shows you what the website gives you as a result. So it tells you that it finds the connectivity with 10, which are here. It finds the symmetry. It finds the same list as topology I showed before. And then down here, it just filters out and finds this tree. This is actually a very rare topology, and that's what is driving us to see if actually we are able to have this type of MOF that wasn't made before. So just a new topology. And again, I didn't do the synthesis, but Lacar, which was a postdoc, again in the Anderson lab, made this MOF. And then I made the computational structure, which is here, and then to see if we obtain whatever experimentally we have obtained, we do again the PXRD overlap between the two patterns. In orange, the experimental, and in black, the computational. And as you can see, the two patterns, they overlap pretty well comparing, considering that the example from before. The only peak that actually is a little bit overshooting is this one at around 10. But I noticed that that peak goes up and down based on the rotation of these linkers, since they're like a little bit flexible and they're cyclohexane, they can rotate very, very easily. So I think after like a better refinement, we could obtain a better matching. And this could be exciting if we actually are able to obtain the same structure as predicted computationally, because it will fortify the workflow that I made. But so far, we have only a PXD matching that can tell me maybe. And so because of these difficulties always of considering the synthesis and whatever can happen during the synthesis of this material, there is little connection in between this workflow that just creates a perfectly pristine and clean structure with what actually happens in the experiment, in the reaction flask. So I decided to do this project that it started first from my curiosity, and then since it's expanding into something bigger, I decided to create a website. So using large language model that they can see previous synthesis of MOF and COFs and see if it can help us giving them what we want as a reagent and as a, for example, topology or whatever information we have to connect the computation that we can make with the experiment. So a bit of motivation for can we actually bind synthesizability and LLM? So are LLM actually able at some point to understand or to actually kind of cross a different type of information from previous literatures and telling us, yeah, you can obtain with this recipe, this type of MOF or COF. So this is what this project that I'm carrying out is trying to understand. So since incorporation of properties like framework stability, building blocks decomposition, reaction conditions, sensitivity to whatever we have, like air or moisture, solvent effect, post-activation, crystallinity, all of these features, they are almost impossible to be implemented into just a structure. It's something that comes before or after, but not in the structure itself, like as I show so far. Also, searching within literature sometimes to take inspiration from other syntheses when we have like a new framework that we want to make is time consuming. And sometimes it's very difficult to find all the literature that actually talk about something similar for many reasons, mostly because there are too many publications so far. So if we actually use some computations on large language model, we can help ourselves to compare different syntheses and maybe mix them to see if we can have a tailored procedure for our case. And another thing that you can tell me is like there are already large language model implemented from OpenAI to Claude to the meta models that they can answer to our question, which is true. They are kind of trained with some of chemistry, some of material science, but not all of them. If you try to ask, for example, some less known MOF or something new, like telling them I want to do this, sometimes they just fall into some cases that are the most common, but not really helping you to find a case that is less common because they're not tailored for just chemistry. So maybe if we can tailor for just chemistry, we can obtain better results. Then this implementation that I'm going to also to show you now, try to also achieve another to solve another issue, which is like sometimes we and other groups, they create kind of large language model or agentic framework that they are tailored for material, but they're usually published or uploaded in GitHub, or they're like a package that they require knowledge of Python, knowledge of the environment, so forth, like experimentalist or any other person that is not that knowledgeable into coding or something, they can come into difficulty. So I implemented all of these into a chatbot that is available online. So all of these limited immediate access is overcome, because you can just go on this website that I place here and try. You can just ask whatever you need and see the help that it can give it to you. Here I explain with this image, like in a very, very high level, what is going on under. So there are two bots, two large language models, one smaller than the other, that they are made for two different tasks. The first one takes the input and try to understand the input and what the user requires. And it just do a retrieval augmented generation. So from a database, it tries to understand which are the good part of the information that we might need for the next step to give us whatever the user has asked. So far, the database is composed by 1,500 MOF and 300 COF data from available data, open, scratch from the internet, and include the composition of the MOF or COF, their properties, the synthesis procedure, the DOI for reference, the CSD code, which are the code that they are made from the Cambridge Structural Database. And lately I'm implementing also some smart strings to make like more flexible the understanding in between human and computing, because, for example, some names of organic molecules or organic links are pretty complicated. So sometimes it could be much easier to just give us my string and then the computer can understand. So after we have a retrieval of this data, this first bot gives like a distilled amount of information to the second one, which is like a bigger model, and it has more ability to check if the data that has been provided is actually useful for the user input, which is also given to this bot or not. And lately, this large language model, they have also a thinking mechanism that we can use, and we can actually slightly tune for the task that we want. So in this case, this bot has a thinking mechanism that try to understand chemistry, like, is this information valid, is there something missing? And then it will iterate with the previous bot and requires if something is missing or if something was not similar to the user input, and then create an answer for us. So here I just give a few examples. So I just try to chat with it, and these are the question and answer that I ask. You can see the full example if you go to the website here. There is a page of examples, so you can read or you can try yourself. It's free. It's implemented there. The only thing is like it's a small server, so sometimes it's slow. But for the rest, so far I'm pretty satisfied. But for example, one of the questions I gave is like, what MOF do I obtain with a zinc node and a BDC linkers, which is benzene carboxylate. And then the model gives us already that we can obtain, for example, MOF5 or zinc BDC, that there are slightly difference, the DOI. And then the bot is pretty chatty, so usually it asks or it suggests what we want next. And then I can ask, what are the characteristics of absorption of this molecule suggested? And among others, it said the CO2 is the best with no hysteresis. But this absorption wasn't the best. So I could ask, what is a modification that we can give to the linker to increase this CO2 absorption? And actually, as is already well known, amine groups are very good for CO2 absorption if we have them on the linker. And indeed, also the bot here is telling us that if we add amine or hydroxyl group, or, for example, other modification based on other MOF, we can achieve a higher absorption. The same thing we can do for COF. We can also ask this type of more philosophical or like more difficult question, like, what is the best cough that you know, for example, for hydrogen absorption. And here, for example, it gave us cough JLU2 as an example, or as the candidate among others that they are there. So I decided to ask, okay, what is a functionalization that they do post-synthetically to obtain this higher hydrogen absorption? And then here again, it gave me like how we can modify the linker using a different linker with hydrazine linker, introducing polar functional group, and so on and so forth. Like also like depositing metal into it. There are some recipe that he gave to us, and also like other coughs. So during the conversation, also since he gave us different synthesis protocol, I asked to compare them. And this is actually one of the results. He compares and he tells us what is the difference, what are, for example, they are made at the same temperature, but one is 3 days, the other is 72 hours, and all of this information that they can be useful if we have a new synthesis, but also they can be useful if we are doing like new synthesis and we want to have a quick some quick data, some quick description of what is already out there. But then also we can have something more easy, like if sometime, I don't know, during writing of a paper, we have, what is the citation of a certain MOF, or I want to see the framework of another certain MOF or COF, so we can ask directly what is the DOI, or I actually try to instruct the large language model, the model, to give, when possible, the DOI, so that the user at the end reading the description can also go through and see and check, because I mean we cannot always be 100% sure of what is the source. But like also having the code from the Cambridge structural database can be very useful, because we can see the structure, and it's a very quick retrieval that sometimes is more difficult, rather than Googling and clicking on a few papers, where some of them, for example, they have been published later, so they don't have the structure. This is somehow faster. Okay, so this is a project that is going on, so it's not finished, and so I will appreciate if any person that try can give me the feedback, or if there are properties that I didn't think of that we can implement. I'm totally open for it. So I dedicate some of my free time to do this. So usually the updates, they come slowly, but so far I'm, for example, expanding the data set, not only using like openly available, but also contacting companies or other institutions to ask if they have database that they can share with me, and be able to kind of augment the knowledge, or let's say the library that the bot has on access. But actually, sometimes it's difficult just only to give instruction or to give information and data to have a very accurate answer, because sometimes something is missing. So the next step is to fine-tune an extra bot that actually knows perfectly and only what MOFs are or what COFs are. So it can answer only to certain questions and include, for example, structural feature or other more information that can be useful for having a better and better answer. Or, for example, if you want at some point to have a 3D structure, it can also give the 3D structure directly to the bot or to the answer to be downloaded or visualized. Okay, so as a conclusion, I mix all of the conclusion from both the workflow and this chatbot. So the workflow is a quick way to obtain MOF and COF without training machine learning models. Sometimes we rely on machine learning, but we could also do a step back and see if actually something can come before machine learning, and then maybe can make the training of machine learning easy, or we can also avoid it sometimes. It allows the most likely structure for further computation and comparison with PXRD pattern. And then after this, if we use some LLM, we can have some synthesis assist computation that we can give, that we can automate and actually have answers from synthesis, from LLM, from previous data that can connect the two, a structural information and an experimental information. The workflow and the chatbot are not perfect. They actually miss a lot of pieces for different reasons. Some is because I didn't code them yet, or they are a bit too difficult. Other is because the code that runs in small servers to be very efficient. So sometimes it requires a bit more time to be implemented. So at this stage, for example, the workflow relies a lot of pre-optimization of the building blocks. So I'm trying to implement like a very quick optimizer of the structure that takes care of the symmetry. So even if somebody that use the workflow is not very well skilled at create the building blocks, they can just be an idea, and then the optimizer will refine them. Then also raw node to the structure and what the structure are still not there. They will be there, mostly the 2D soon. And also some integration with other analytical measurement, for example, PXRD. So far, we do the PXRD at the end. So we obtain the structure, we optimize, and then we do the matching. But what if the PXRD can also be uploaded, and then it can be like one of the channels inside the workflow, and then we can also have a refinement of potential topology or symmetry from the pattern itself. And then, as I said, the chatbot will have some extra feature, one of which is the smile stream, that it should come very soon. And okay, so if you have an Imhoff that you want to predict, please go and use these two applications. They are both online, free, available. There, either the chatbot or the workflow. And if you have any feedback or requirement suggestion, please let me know. And thanks for your attention.
Thank you, Andrea. So please thank Andrea for the nice talk, physically or virtually. I'll